Okay, yeah, thanks to the organizers for the chance to visit and the chance to speak here. So my talk is in some sense, well, the most related of the previous ones to Pierre's and Ivan's. But in contrast with them, I'm going to try to say something about models beyond exactly solvable ones. So predictably then, what I can say so far is very modest, but you'll see. So I'll start with describing some variational formulas for the limiting free energy and time constant in directed percolation and polymers. And this will lead us into something called Boseman functions. That it's a notion from geometry of metric spaces, but it's been introduced in percolation about 20 years ago and has been gaining in popularity ever since. And once we've gotten into these Boseman functions, I want to show a few ways in which these things play a role in these KPZ class systems. Okay, those are my collaborators, Firas from Utah mainly, and then Nikos, an ex-student, and Attila from Istanbul. Okay, so let me begin by taking a few moments to describe the model. It's very familiar to most of you, but at least need to establish my terms here. So there's a piece of the integer lattice on the plane, and I'll attach random weights to each of those points, IID. So we get our random medium or random environment. So no assumption on the distribution at this point. At some point, I'll put a moment assumption on the omegas, but nothing more. Although I have to admit that in the end, I'm going to revert to the exactly solvable models to really flesh out the stuff I'm going to say. But for a while, it's quite general. And then we consider increasing paths, right? Lattice paths that takes nearest neighbor steps up and to the right. And a path has a weight, of course, that consists of adding up the weights that it collects along the way. And if I want to then describe a directed polymer model, let me fix two points on the lattice, a u and a v, and then consider all the paths that go between these 2 points, and take an inverse temperature parameter beta, and then I'll define a probability measure, right? The quenched polymer measure on those paths gamma that go between u and v. And the key object is, of course, as always, the partition function z of u and v, sum of all those paths. So there will be 4 different models I'm going to describe. So that's the point-to-point polymer. And then, of course, there's the point-to-line polymer, where I fix only the initial point of the path, but consider all the paths of a given length. And it's convenient to throw in a sort of an external field parameter h or a tilt. It'll be useful later on. So there's the partition function for that version. So I've fixed the initial point at the origin, and then I consider all the paths of a given length n, and then sum up the exponentials again with the weights of the path there, and then this external field term at the end. So that's 2 out of the 4. And then we get into directed percolation by taking beta to infinity, right? The 0 temperature polymer. So 2 more things here. So first, for the point-to-line version, think of beta inverse log z, take beta to infinity. Then we get to the model where all the weight is put on the paths that maximize, all the probability is put on the paths that maximize the stuff in the exponent. So then that's this version here, and I'll call that quantity capital G, although it won't really appear that many times. So this is last passage percolation, right, or the corner growth model. And then there's one more thing, which is the point-to-point version of the last passage percolation. So again, fix 2 points on the lattice, and then just maximize weight between those 2 points. Right? So 4 models, right? 2 positive temperature polymers, point-to-point and point-to-line, and then 2 0 temperature polymers, point-to-point, point-to-line. And first, what do we start looking at? Well, large-scale behavior, right? So let's look at limiting free energy and limiting time constant. So here's first the point-to-line case. So what's going on there? The familiar thing, right? There's the partition function again. I threw in a factor 2 to the minus n there just to make these sums into expectations over random walk paths. It's sometimes convenient. And then log in the front 1 over n gives us a limiting function g of h So it's a deterministic function, nice Lipschitz continuous convex. And then the same thing for the 0 temperature case, the last passage percolation. So there's a superscript infinity there to distinguish the two. So I'll be using this notation in the sequel, and it's convenient because then I can talk about both at the same time simply by considering all the possible beta values, from 0 to all the way to infinity. And then there are the point-to-point counterparts, right? So now I have to fix a direction xi. So let's take it from this simplex here. And here, sum over all the paths that in n steps go to a point close to n xi. And then again, the same limiting idea. And here's the point-to-point directed percolation case. Again, go in direction n xi and take a limit. So this again is a perfectly nice deterministic function of xi. It's concave and continuous on this set of directions here. So that's the setup. Any questions at this point? So let's try to say something about these limits. The first observation is that they're in a nice duality, the point-to-point and the point-to-line case. It's really a large deviations duality for those of us who like large deviations, because if I look at the quenched, oops, sorry, wrong button. If I look at the quenched polymer measure of a point value like this and take the limit, then I get basically the point-to-point free energy subtracted by the point-to-line thing because of the normalization. And on the other hand, the cumulative moment generating function is the point-to-line thing. So there's basically the rate function and the limiting generating function, which are in duality in large deviation theory. Hence we get this duality here, which then associates between, there's then this association between the directions xi and the external fields h, which will show up a little bit later. But the question now is are there any formulas or descriptions that I can give to these limits? So the issue is that they're subadditive limits, right? They don't come from the familiar additive ergodic theory where it would be obvious. They would be just expectations. But here there's something more complicated. So as a warm-up, let's look at a finite case. So the finite case would be not the IID environment case, but a periodic environment case, so a special case of an ergodic thing. So here's an example. There are 6 different environments, right, that you get by choosing where you put your origin or shifting them around. So let's define a matrix to describe this. Don't have to necessarily look at that too carefully, but it's like an incidence matrix. I'll put a non-zero entry at omega tilde in case omega tilde comes from omega with one of these admissible steps, and then put the e to the omega 0 there. And for simplicity, I'm dropping the h, and I'm also putting beta equal to 1, just to not make this look too messy. And then if I want to take the limit of the free energy, it's simply the same as raising that matrix to a power. And when I take a limit, of course, I get the log of the Perron-Frobenius eigenvalue. Right? So it's an irreducible positive matrix, non-negative matrix. So there it is again, the same thing repeated. So now if I want a formula for this limiting free energy, I can just look up any formula from textbooks for the Perron-Frobenius eigenvalue. So there's one of the ones one finds, right, the min-max formula. So let me turn this into a formula for the free energy. Just take a log, and just to anticipate a little bit what comes next, let me rewrite it slightly. So because the matrix A contained the condition of going from omega to omega tilde with admissible steps, so then once I write phi as e to the f, it becomes a shift. It becomes sort of a gradient, a difference of 2 shifts in the exponent. So let me write it like that and highlight that point just to illustrate, just to make a connection with what comes next. Okay. So what is the generalization of these gradients once we go to the infinite dimensional case? Well, here. Oh, let's go back. It's just algebra, nothing more. See here, you're basically just oops, sorry, wrong button. You're basically up here. You're where's my dot? You're multiplying exponentials, right? These exponentials, and you're multiplying them over admissible paths. So if you raise this matrix to a power, you end up doing the same thing, multiplying those exponentials over admissible paths. So it comes out like that. Right? Okay. All right. So let me next show you what the generalization of this formula is for the infinite dimensional case. So these gradients generalize as follows. Co-cycle. So think of a general situation now where you have a probability measure that's invariant under this group of shifts. So here's a notion that we can call a co-cycle. So it's a function that takes 3 arguments. There's a point from the underlying probability space, so that's the space of environments. And then there are two lattice points. And what I want this thing to satisfy are integrability, a certain kind of stationarity. In other words, if I'm shifting these lattice points here, that's the same as shifting the underlying configuration of weights. And then this co-cycle property, or this additivity. So going from x to y plus going from y to z has to be the same as going from x to z. So call these co-cycles. And in particular, if this thing has mean 0, then let's call it a corrector. So this term, we chose it for this use because this is a little bit analogous to what happens in homogenization of PDEs or in central limit theorems of motion in random media, where you have these kinds of functions appear. Let's see. No, I don't know. No, it's built into. I have 2 arguments. See, I have two spatial arguments. Yes, you're right. If I had 1 spatial argument, then definitely yes. All right, and this is well, obviously, almost obviously, right? Pretty obviously, gradients would be a special case of this, and you get them all by taking L1 limits of gradients. So it is sort of a natural generalization of those gradients. And so here's a variational formula for this point-to-line free energy. So there's the definition again, the limit, and here's the formula. So it's exactly what went before for the periodic case, with the only difference that now instead of that gradient, there's this corrector. And it turns out that the minimizing thing always exists. One can prove it by taking a weak limit of averages of increments of these free energies on the lattice. All right. So there's a formula for the so it's the positive temperature polymer, the point-to-line case. There's a corresponding formula also for the point-to-point case, but let me leave that out and just focus on the point-to-line case just to keep this a little bit under control here. So let's next go to the percolation case. Oh, okay. I see. Yeah, I guess I should of course clarify. Right. What is this saying? So there's an infimum over these correctors. There's an essential supremum over the space of environments, and that this bold P here is the distribution. It's the background distribution, the IID distribution on the environments. So these omegas are. Yeah, that's right. That's right. So this is an infinite weight configuration. And this thing, of course, typically it's not in any way local. It's going to look way into the asymptotics. So it's a complicated function. Okay. So the way I've stated it here, I've stated it now only for the simplest possible geometry, right, of the 2-dimensional polymers. But it's really valid quite generally. Go into any dimension, take an arbitrary kind of walk, and the underlying P, this bold P, doesn't have to be IID. It can be mixing or even merely ergodic. But to compensate, then I would have to put stronger moment assumptions on omega 0. And now I realize I didn't write the moment assumption anywhere so far, did I? So this is true if omega has 2 plus epsilon moments. But if you want to make P less mixing and more merely ergodic, you need to increase the moment assumption. And if you want to go all the way to merely ergodic, then omega has to be bounded. All right. How do I interpret? So this is a sum over all the admissible steps. But in this case, the admissible steps are just E1 and E2. Okay. Or I guess it's an average since I have the 1/2 there. It's like a transition. It's like a one-step transition in the underlying random walk. Either right or up, and then computing this function. That's right. There's no expectation, just the essential soup. Yeah. And what we'll see then when we get to the cases where we can really see what goes on in this formula, it turns out that this essential supremum even falls out, and this entire function here turns out to be almost surely a constant in omega. Does what depend on the dimension? Yeah, it's the same formula. It's exactly the same formula. Yeah. All right. Yeah. So yes. There's always.
So when you say other types.
Yeah, that's right. No, it's fairly. No, it actually doesn't. We can at this level we can prove the theorem without assuming that the walk is directed. Any finite set of steps. Any finite set of steps. And yeah. All right. So let's go to the. Okay. I did have a line of proof here. So this comes from large deviations, and in what kind of large deviations? So here is an empirical measure that operates on the space of environments cross admissible steps. And what this empirical measure is registering, it's registering what a random walk would see as he is traveling along in the space of weights. So from RW, from random walk in random environments, this is the kind of thing we look at there all the time. See, there's the environment shifted by the position of the walker. So the environment as seen by the walker, and that's his next step there. So the random walker is marching around on the configuration space, looking around to see his environment and keeping track of his next step. So by developing a large deviation theory for this kind of a object in the quenched sense, so under a fixed omega, that's where these results are coming from, basically. Okay, and then to the last passage, percolation. So there's the definition again, the limit of the point-to-line percolation value, the time constant. And we can also get it by doing first the finite temperature thing and then taking temperature to 0. And so if I take temperature to 0 in the previous variational formula, I get immediately a formula for the percolation case too. So what you see happening there is that where you had a log and a sum and an exponent, so it just all that just simplifies into a maximum. Right? And otherwise it works the same way. Okay. Well, let me also pair. So a moment ago we looked at the finite case for the positive temperature polymer. So that was the periodic environment. Let's look at the periodic environment here too. So it's still Perron-Frobenius theory, but now it's not the classical one. It's the max plus type. Yes. Well, at this point, yeah, it's just nice to have a variational principle. So of course, the hope is to try to do something more, and at this point we can flesh out this stuff only for the exactly solvable cases. So we're in the process of working out something for the more general case. Yeah. So this was the sense in which I used the word modest when I began. For, sorry, what? Well, yeah, I don't know. Yeah, no, it's no, but no. So you're pointing towards the questions about the curvature of the shape, and no, don't know yet. Yeah, no, that would of course be a great coup to be able to say something about that. Yeah. Probably not, but we haven't really addressed that, tried to address that either. Not sure. Okay, so let's just take a look at the periodic case for the last passage percolation. So now again, I dropped the external field just to make this a little bit simpler. I mean the periodic environment. Oh, periodic environment. Yeah. So finite omega space. So here's the limit again, and now I can write it in terms of max plus algebra. So A there is an irreducible max plus matrix defined like this here. Again, sort of an incidence matrix. So I put the weight there if omega tilde can be reached from omega by an admissible step. And then if you look into the max plus literature, you find that this kind of a matrix, irreducible, it has a unique max plus eigenvalue lambda with an eigenvector sigma that satisfies this. This is their version of the eigenvalue equation, right? Where we'd normally put a sum, we put a max now, and where we'd normally multiply, we put a plus now. And so this thing exists, and they've got their theory for it, books and things. And if you pair up this equation with that limit there, you see that the lambda, the eigenvalue, is again the limiting time constant. And just like before, this is exactly our variational formula right from a moment ago, and it's again a gradient that minimizes it. Okay. Well, let me just a brief historical sort of slide here. I haven't talked about first passage percolation at all, right? But that, of course, was sort of the original model that came already in 1965 in the work of Hammersley and Welsh. The origins of last passage percolation are kind of murkier, and maybe the first time when something like that was in the literature is in Rost's 1981 seminal paper on the hydrodynamics of asymmetric exclusion, although at the time the last passage description didn't seem to be known to Hermann Rost, because at least he did not mention it. So that seems to have been discovered then later. But it is the case that no formulas for the limits have existed until now. And then it happened independently twice, distinctly. So unbeknownst to either one of us, either parties, Arjun Krishnan, a grad student of Raghu Varadan, was developing an analogous variational formula for first passage percolation. And we finished our works at roughly at the same time, and nicely, since he's a student, his was 2 weeks before ours, so that was I think the proper order of things. But the two works are entirely different, actually. Well, not entirely, but fairly different. Krishnan really relies on the homogenization of Hamilton-Jacobi PDEs, and as I mentioned, we come from the probability side, from large deviation theory. Although we do also borrow some technical ideas from Jelena Kosygina's and Raghu Varadan's homogenization work. Okay. All right. So here's a summary again of what we have here so far. So again, the limits: positive temperature polymer, the last passage percolation, the limiting definitions, and the variational formulas. And as I mentioned, there are counterparts of the formulas for the point-to-point case also. And as already pointedly demanded by Jürgen, of course, want to understand something about these formulas. So let me then switch to some exactly solvable model to actually illustrate a little bit what goes on here. In particular, where does this minimizing corrector come from? And that's where the Busemann functions come in. So which exactly solvable model to take? Well, for last passage percolation, it would be the one with the exponential or the geometric weights. For the directed polymer with this geometry, it would be the log gamma polymer. So let me pick the log gamma polymer for obvious reasons, since I happened to come upon it a few years ago. So here's the definition. IID gamma distributed weights. That's what the distribution looks like, in case you forgot. And let me pull a small change of notation on you. So when I write these partition functions, instead of writing exponentials of sums, for this model it's nice to write products of reciprocals of the weights, simply because then the weights are gamma distributed, and then aspects of the gamma beta algebra random variables very nicely comes in and makes formulas attractive. Okay. And why is this model special? So two reasons. There's a connection with combinatorics through a sort of a geometric version of the Robinson-Shenstedt-Knuth correspondence. Now that will be a separate talk, so I won't go there at all. You got a small glimpse of what this points to in Ivan's talk when he talked about the bigger algebraic picture of exactly solvable models. This model, of course, lies in there, and it's a particular specialization of the big picture of that Borodin and Ivan have been developing. The feature that I want to focus on now is that there is a stationary version of this model, by which I mean that there's sort of a stationary version of this process of point-to-point partition functions indexed by the points on the lattice. So actually, let me just describe to you what that looks like. So I'll build this on the first quadrant of the plane now. And now I have two parameters. The rho is the parameter fixed a moment ago for those IID weights. And then there's an additional parameter alpha that parameterizes the boundary conditions that makes it stationary. So here's the bulk. I'll put there again gamma rho weights. And then I'll put weights on the axes. So on the x-axis, I'll put some edge weights. And these edge weights are gamma alphas. I'll do the same on the y-axis. I'll put edge weights there, and these ones are gamma rho minus alpha. And then again, I'll consider paths that start at the origin and end up at some point v. And now, of course, every path will collect two types of weights. Some weights on one of the axes, either the x-axis or the y-axis, and then it'll jump into the bulk and collect some bulk weight, right? So when I write down the partition function, it has weights coming from those two sources, right? So let me put a superscript alpha there to distinguish this partition function from the earlier IID one. So first it collects a bunch of weight on one of the axes, reciprocals of those taus, and the capital T there is just the time that it spends on one or the other axis. And once it hops into the bulk, then the walk collects the remaining weight along its way to V, to the point V. So define all these partition functions, and then, well, what is the sense in which they are stationary? So here's the precise sense. Define these ratio variables for each x and y, and then take logs to make them additive. And this turns out to be a stationary cocycle again. In other words, the picture stays the same no matter where you shift the origin. In particular, the distribution stays the same. So those distributions that I built into the x and the y axis, those are repeated all over the lattice. So in particular, the horizontal edges have gamma alpha weights, and the vertical edges have gamma rho minus alpha weights. And then if you look at an axis, they're all independent. But it's not all independent, of course. If you have to look at it, you have to look at particular paths on the lattice to see independent weights. And if you look at the wrong kinds of paths, they're not independent. And this, yeah, the same thing as always. Yeah, any path that takes steps only to the right and down would see independent taus along the way. Yeah, yeah. So this is obviously useful, right? We have explicit distributions we can calculate. So now let me just show you a few things that we can get out of this. So let's go to these Boseman functions now. So these were, like as I said this already, they were brought into percolation by Chuck Newman in the mid-90s when he was studying geodesics of first passage percolation. So what are these things in percolation type models? Well, you take the passage time variable, fix 2 points x and y, and then take the endpoint v to infinity in some particular direction, and hope for a limit. That's this notion in percolation. And what Chuck proved at the time was that if you allow yourself to make some strong uniform curvature assumptions on the entire shape, then these limits exist almost surely. There's been notable progress since, but only very recently. So this was the state of the art for almost 2 decades. And then recently, Michael Dameron and Jack Hansen weakened Chuck's conditions quite a bit. Well, weakened the hypotheses that Chuck needed in order to get results on geodesics. And the novelty that Michael and Jack used was that they did not insist on almost sure limits of these Boseman functions, but rather just weak limits. And out of that, they were able to get much of the same information about geodesic that Chuck had been able to get. But of course, here, now I'm in an exactly solvable model, so none of these considerations matter because I have all the information I could possibly want to have. So it's just a matter of sitting down and proving that these Boseman functions exist. So fix a direction xi and consider a sequence of lattice points v that's going to infinity in that direction. And then the statement is that this limit of differences of log z values exists. And again, it defines a cocycle, a stationary cocycle. And the distributions are the ones that we've seen already before on the horizontal edges, the parameter alpha, and on the vertical edges, the parameter rho minus alpha. And when you pick a direction xi, of course, that picks the parameter alpha. So this is an equation that arises along the way that tells you how the alpha is chosen. These psi naught and psi 1 are the digamma and the trigamma functions. So the digamma function is the logarithmic derivative of the good old gamma function, and then the trigamma is the derivative of the digamma. And I see there should be a subscript 0 down there. Sorry about that. So getting this limit is a consequence of having that stationary system, because one possible way of getting it is to couple things with the stationary version. So you, of course, when you couple, you want to choose the right parameter for the stationary version. So you pick a parameter a little bit bigger than the correct one and a little bit smaller than the correct one, and then you get some comparisons, and this way you get the limit. See, the stationary version, it gave us direct control over the ratios of these z values, because those were the very variables that were involved. So we get cocycles out of these Boseman functions, and the cocycles we get are the ones that minimize those variational formulas that I showed before. So here's again the point-to-line variational formula, same one as before. So here h is given, right? We pick a value of this external field parameter. So to pick the right Boseman function, I have to pick the right direction to go into. So this is where the duality comes in that appeared in the early part of the talk. So given the h, pick the xi so that the duality is satisfied. Take the Boseman function in that direction. That's not a mean zero thing, so I've got to center it in the right way. So that vector h of xi there is simply the mean of the b thing. And that this way I get a corrector, and then the result is that it solves the variational formula. And like I mentioned before, the essential supremum over omega even disappears. So this expression on the right is constant almost surely, and that is the constant there. And we can also get it completely explicitly in this case, of course. So that's what it is. Say the h1 coordinate of the h minus the digamma function evaluated at this alpha of xi, where the alpha of xi was the parameter chosen by this direction xi on the earlier slide. Okay. So that's one thing that the Boseman functions give us. They solve these variational formulas. So let me mention a couple other things that the Boseman functions give. They also reconstruct the stationary polymer itself. So remember, the stationary polymer had two ingredients. It had the bulk weights and the right boundary weights to make things stationary. I can define all that stuff just from the Boseman functions themselves. So here's what I do. On the boundary, I put either the negative Bosemans, and I have the right distributions. In the bulk, I can't take the original bulk weights now. I have to define a new version of the bulk weights. So this is what I do here. And it works just right because I've got a gamma alpha there and a gamma rho minus alpha there, and they turn out to be independent. So it's a gamma rho when I add them together. So these ingredients create another version of that stationary log gamma polymer model. Well, the original one gave the Boseman functions by limits. So I guess what I'm trying to say is maybe rather on these lines here. So you can imagine this Boseman limit actually in the following terms, that if you have the IID polymer model, you pick a direction and you go in that direction and you look at the process of log z increments around you, then you will see that distribution converge to the stationary process. So it's an analog of a Markov chain converging to its stationary state, right? So that's another way to view this limit. And the direction you take then of course picks a particular parameter value for you. So that's another aspect of the Boseman functions. And let me also mention the fluctuations. So this stuff is now a few years old. For the cognoscenti, this is old, but I think it needs to be mentioned here anyway. So we've heard now what the KPZ class is like, right? It's characterized by fluctuation exponents, 1/3 if you look at the log z or the time constant of percolation, and 2/3 if you look at paths, and limit distributions come from random matrix theory. So these kinds of considerations that I've been talking about here, so working with the stationary process, that's good enough to give the exponents, right? But it's not good enough to give limit distributions. So to get limit distributions, you need something a lot heftier, like what Ivan was showing us today. So in particular, if you use the connection with combinatorics that I alluded a moment ago that the log gamma polymer has, then one can convert probabilities into Fredholm determinants and do asymptotics. So this is in particular something that Ivan did with Alexei Borodin and Daniel Remenik a little while ago. So one can get the Tracy-Weedom limit for the log gamma polymer that way. But let me show you just a couple of theorems about these exponents, since that's what can be obtained from the techniques that I've described so far. First, the stationary case. So if I want to see the KPZ exponent 1/3 for log z, and I'm in the stationary system, I have to pick a particular direction. So this is the same equation that actually appeared just a moment ago, where that shows how a parameter value alpha and a direction xi are coupled together. So in case you're wondering why, the reason is the following. Once you've put down your boundary weights in that polymer picture on the lattice, what happens is that those boundary weights are larger than the bulk weights. See that the bulk weights had parameter rho, and these boundary weights have smaller parameter, but they're reciprocals of gammas. So the boundaries attract the path. So now there's exactly one direction. If you force the polymer to go into a particular direction, there's only exactly one direction where the typical path spends macroscopic time 0 on the axis. And that's the one where you see the KPZ exponent. Otherwise the central limit fluctuations of the boundaries ruin everything. So that's why I have to take a particular direction. And there you see then the KPZ exponent. So the variance of log z is of order n to the 2/3. And then by coupling again, I can push this result onto the IID weights case. So the result is a little bit weaker, right? The power p doesn't go all the way to 2, but anyway, it's good enough to establish the size of the exponent. And maybe lastly, let's ask the following question. So when you write down these quenched polymer measures, right, they're not marginals of a given fixed measure. You have to write down a different measure for every value of the length of the path. So an obvious question is, what if I take the length of the path to infinity? Do I get some kind of a nice limiting measure? And this question is simple in weak disorder, right, because of Bolthausen's 88 result that says that already the normalized partition function converges. So it's easy to take the limit and see the random walk in random environment appear. But with these Boseman, once we have the Boseman limit, we can do the same here in strong disorder also. So let me use the Boseman functions to define this transition probability here. The fact that these two denominators agree is just an immediate consequence of the way the limits are, the Bosemans are defined. There's no mystery there once you write it down. So let's consider now the point-to-line quenched polymer measure with a particular h value there, and take a limit of this as n goes to infinity. So the theorem is that it goes to a random walk in random environment whose transition is given like this here. And again, it's the same business that once you fix h, then you pick the direction c that's dual to h in that earlier duality. And how does the proof go? Well, modulo a certain limit is just a few lines. So here's my so fix a segment of path of length m. So m is fixed, n goes to infinity. Rewrite the quenched measure a little bit. So the rest of the path is free, right? So I get to add over that. So that gives me another copy of the partition function, and write it as a product of ratios of sort of nearest neighbor shifts that differ by nearest neighbor step. And then you need to prove a little bit. So it turns out that these ratios of point-to-line partition functions also converge to the same Boseman functions, once again, with a little extra piece coming from that random field term. And then in the limit, you just notice that this is exactly the product of those transition probabilities. Okay, I see. I guess I'm doing pretty well with time. This was a possible endpoint for my talk, but since you've allowed me to go so fast, I'm going to impose another 3 slides on you. So we have another set of variational formulas for these models, which are in a sense dual to the ones that I've shown you so far. We just have the formulas, though we don't understand. We understand even less about them presently, but I'll show them to you. They are more natural to those of you who come from a large deviations background like I do. So here are the definitions of the limits once again. Remember the translations. And now do the following. So earlier I briefly showed you that that empirical measure whose large deviation theory was behind those previous results. So here's the transition probability for that Markov chain. See what this formula here is saying is that on this space of environments cross admissible steps, you keep track of your current environment and one step, and you move forward by picking a step at random, using the previous step to shift the environment, and then picking the new step as the next one to keep in store, right? Let me summarize this operation by this with this transformation S sub ei. So that's a Markov transition on that space, and there's a natural relative entropy that's used in large deviation theory. So take a measure mu on that space and think of a transition kernel Q on that space, and then form the measures mu cross Q and mu cross P. P was the original transition from a moment ago, and there's the relative entropy. So I'm thinking now of only of Q's of the form that they're supported on these on these transformations SEI that I defined a moment ago. Now, so that's the relative entropy that one would use in the large deviation theory of Markov chains, but it doesn't pay any attention to the background measure P. So it's not quite the definition we want. So in order to get an entropy that respects our environment measure P, I make the following definition, that those measures mu whose marginal is absolutely continuous with respect to that background measure get this entropy, and the rest get infinity. Okay. All right. And here are the variational formulas then. So on this space of omega cross steps, there's a notion of an invariant. Among them are something that we might call invariant. Invariant in the following sense, that if you just look at the expectation of a function of omega alone, then that's the same if you translate with that random step. So capital Z here denotes the sort of the random variable that denotes the step on that space. So those are the measures that appear in these variational formulas. So for positive temperature polymers, we have then this formula here, which is of course looks very familiar to anyone who's ever done any large deviation theory, right? So just like something coming out of Aradan's theorem, expectation of the energy thing minus the entropy. And then when you go to a directed percolation, I want to take beta to infinity, so the obvious thing happens, that part just drops out. And we have this formula for the point-to-line limit of the directed percolation model. And so a priori, I thought that this would be the formula to work with at first. But this is actually a little bit annoying, because this absolute continuity condition here throws away all compactness once you're in an infinite space. So we actually don't yet know much about how these formulas behave. We know what they do in the finite cases. It's again just part of the Perron-Frobenius picture. And we know what they do in weak disorder. So that's in dimensions 3 and higher and with high enough temperature. But we don't yet really understand how they behave in the strong disorder case, even for our most beloved explicitly solvable models. So that remains to be studied. Well, now I'll really stop. So thanks very much.